Can you derive the transfer function? So yesterday we have derived one transfer function for a tank. So can you derive the transfer function? This is Q. This is Q naught. Where Q is equal to H into R. Yesterday we have derived transfer function if the resistance is H by R. So what is the transfer function? So transfer function means you have to write in the form of Kp by tau s plus 1. This is the standard transfer function. For first order systems, Kp by tau s plus 1 is the standard transfer function. So how do you derive? So you will write the model, let's say rho q naught equal to rho q plus d into rho into a into dh by dt. Rho will cancel on both sides. Q naught minus q equal to a into dh by dt. Then what is h? Q? H into r. So q naught minus h into r a into dh by dt. So if we write the steady state model, hs into r a into dhs by dt, which is equal to 0. So from this one you can derive deviation variables q naught capital H into r a into dh by dt. Now we apply Laplace transform, Q naught of S equal to H of S into R, A into S into H of S minus H of 0. What is H of 0? 0. Because the deviation variables initial values are always zeros. Because how do you write the deviation variables? H is equal to H minus Hs. H of 0 means H of 0 minus Hs. But H of 0 is nothing but Hs only, no? Hs minus Hs, which is nothing but, let's say, 0. So what is left here is Q naught of S minus H of S into R, A into S into H of S. Now if you rewrite the terms, Q naught of S minus H of S into R is equal to AS into H of S. What is H of S by Q naught of S is 1 by AS plus R. But this is not the standard form. Don't write like this. This has to be written in the form of KB by tau S plus 1. So to write in this form, A by R plus 1. So 1 by R will become your KP. A by R will become your. So this is the derivation. Another example of what is KP and tau, I will tell you. Another example. So we have tried one example. So another example of first order systems is thermometer. Thermometer is also one of the examples of first order systems. What is meant by first order systems? So when you write the dynamic models, you will get the single differential. Is the basic definition of first order systems. So thermometer is also one of the examples of first order systems. Can you start writing the model for a thermometer? Just develop a model for thermometer. Suppose if we have a thermometer, let's say have the thermometer. So it is, let's say, reading 25 degrees now. So you have the mercury reading, which is at, let's say, 25 degrees now. So suddenly you take this thermometer and put it in a temperature bar, which is at, let's say, 100 degrees centigrade. Then what happens to the thermometer reading? The thermometer reading will also reach ultimately 100 degrees centigrade. So what is the process that you understand in thermometer? Suppose if we draw the cross-sectional view of the thermometer, let's say this is the glass and inside you have the mercury. Heat is transferred from outside to the mercury because the entire outside ambience is 100 degrees, whereas mercury, which is at 25 degrees centigrade. Clear? So this is the steady state of the thermometer. This is the steady state of the thermometer, which is initially at 25 degrees centigrade because ambience is also 25. Thermometer is also at 25 degrees centigrade. Both are at 25 degrees centigrade. Suddenly you take the thermometer and keep in a temperature bar of 100 degrees centigrade. Then what happens? Heat is transferred from the outside ambience to the thermometer mercury. So how do you write model for this one? So what is the heat transfer is? Heat from this one will transfer through mercury like this. This is convection. So this is conduction. This is so this is also convection. So this is convection followed by conduction followed by convection. Clear? So heat will be transferred from the outside ambience into the mercury. So there are three modes: convection, conduction followed by convection. Let's assume that the glass wall thickness is so less. This is negligible. The thickness of the glass wall is so less that, let's say, conduction is negligible, or let's say the resistance of conduction is negligible. Then what is left out is convection and convection. So how do you write the model is heat transferred to the mercury is equal to heat gained by mercury. heat transferred to the mercury is equal to heat gained by the mercury. What is heat transferred to the mercury is HA into, let's say outside temperature is X, inside temperature is Y. Outside temperature is X and mercury temperature is, let's say, Y we are writing. Clear? So H into X minus Y, which is equal to mCp into dy by dt. HA into X minus Y is heat transferred to the mercury from outside ambience, and enthalpy change of mercury is mCp into dy by dt. So this is the model for thermometer. Heat transferred to the mercury is equal to heat gained by the mercury. Just understand this model. Here X is your input and Y is your output. X is your input and Y is your output. So any doubts in this model? So the disturbance here is the thermometer which is at steady state, 25 degrees and 25 degrees. Suddenly you keep it in the temperature bath of 100 degrees. That means the disturbance to the thermometer is now its input is 25 and its output is also 25. Suddenly you are changing the input from 25 to 100, no? Then the output, the thermometer slowly heat will transfer. How does thermometer detect the temperature? Heat will transfer from the ambience to the mercury and mercury will expand. That expansion is calibrated in terms of temperature. That is the function of the thermometer. Clear? So initially thermometer reading shows 25 degrees because the mercury temperature is also 25 degrees. Why mercury temperature is 25 degrees? Because the ambient temperature is also 25 degrees centigrade. Now, suddenly you keep the thermometer at 100 degrees centigrade. So, heat will transfer from the outside ambience to the mercury. Mercury will also reach the temperature of 100 degrees and it will expand. So, it will show the 100 degrees centigrade. Once it reaches 100 degrees centigrade, then you have reached the new steady state. But whatever the model that we have written is the transition from 25 degrees centigrade to 100 degrees centigrade. So the journey of the thermometer from 25 degrees centigrade to 100 degrees centigrade is captured by this dynamic model. So during this journey of 25 degrees to 100 degrees centigrade, heat will be transferred from the mercury or let's say ambience to the mercury through three modes: convection followed by conduction followed by convection. Let's assume that conduction is negligible. Then you have only convection heat transfer. That is why. Then what is the heat balance? Is heat transfer to the mercury is equal to heat gained by the mercury. What is heat transfer to the mercury is Ha into X minus 5, which is equal to mCp into dy by dt. Any doubts here? Okay. So now that you have the model, HA into X minus Y, which is equal to mCp into dy by dt. What is your X? X is your input and Y is your output. Clear? So can you derive the transfer function here? Now what you should write for the transfer function? You should write the steady state model, get the deviation variables, apply the Laplace transform, write output divided by input, and write in the form of Kp by tau s plus 1. So how do you write steady state model? Is equal to 0. So HA into what is y of 0 is 0. So if you write y of s by, so what is your Kp is 1, what is MCP by HA is tau. So write this problem. A thermometer, a thermometer is initially at steady state. A thermometer is initially at steady state at 25 degrees centigrade. At 25 degrees centigrade. Suddenly, it is transferred to a temperature path. Suddenly, it is transferred to a temperature path at 100 degrees centigrade. At 100 degrees centigrade. At time t equal to 0. Estimate the reading of the thermometer. Estimate the reading of the thermometer after 0.1 minutes. After 0.1 minutes. Brackets. Time constant of thermometer is 0.1 minutes. Time constant of thermometer is 0.1 minutes. The question is, a thermometer is initially at steady state at 25 degrees centigrade. It is transferred to a temperature bar of 100 degrees centigrade at time t equal to 0. So what is the reading of the thermometer after 0.1 minutes? So time constant is 0.2. So what is the answer? So now yesterday we have solved one problem. So you take a system, let's say Kp by tau s plus 1, and if you give the input force by A by S, then what is the response is Kpa into 1 minus e power minus t by tau. Now, what is the thermometer? 1 by 0.1 s plus 1 is the transfer function. What is the input? Input is 25 degrees and it is suddenly changed to 100 degrees. So what is the input is 75 by s. Then what is my response? Capital Y equal to Kp into A. What is Kp is 1. A is 75 into 1 minus e power minus t by 0.1. T by tau. What is Y is 75 into 1 minus e power minus 10 into t. So this is the response. Now what is the response after 0.1 minutes is Y of 0.1 equal to 75 into 1 minus e power minus 10 into 0.1. So this is 75 into 0.632. So what is this value? 1 minus c is 0.632. 47.4 degrees centigrade. So what is the, but this is not the answer, no? What is 47.4 is a deviation variable. So what is actual variable is pi minus 25 degrees equal to 47.4. Then what is actual reading is, so y minus 25 degrees is equal to 47.4. So what is the actual reading after 0.1 minutes is 47.4 plus 25, which is 72.4 degrees centigrade. So the thermometer reading is 72.4 degrees centigrade after 0.1 minutes. Now what is the function here? Y equal to 25 plus 75 into 1 minus e power 10 into t. So what is the value at infinity? So 25 plus 75 into 1 minus e power minus infinity, which is 25 into 75. So 100 degrees centigrade. So ultimately it reaches its final value, which is 100 degrees centigrade. So how to give pulse input to a thermometer? Just dip in the temperature bath at 100 and take it out. Pulse means keep it for some time, no? So dip in the temperature bath, keep it for some time and then take it out. Next problem. The unit impulse response of a first order system is 2 into e power minus 0.5 into t. The unit impulse response of a first order system is 2 into e power minus 0.5 into t. So what is the transfer function of the process? What is the transfer function of the process? Now you have to compare first order response Kp by tau s plus 1 with, let's say, what is pulse input? Impulse input is 1. Then what is the response? Kp. So basically, if you have A, Kp A by tau into e power minus t by tau is the response. Now what is A? 1, because it is unit impulse response. Then Kp A divided by tau into e power minus t by tau will be compared with t power minus 0.5 into t. So which gives 1 by tau equal to 0.5 and Kp A by tau equal to 2. So what is tau is 2. What is Kp into A by tau is 2. What is A is 1. So tau is 2. So Kp is equal to 4. So what is the transfer function is? So what is the transfer function is? 4 by 2s plus 1. So next problem. So next problem. The unit impulse response, of an unknown process, the unit impulse response of an unknown process is t into e power minus t. T into e power minus t. What is the unit step response of this process? What is the unit step response of this process? The unit impulse response of an unknown process is t into e power minus t. What is the unit step response of this process? So I will teach the significance of Kp and tau. So there is time. This is not a first order system. This is an unknown process, some unknown process. Only for first order systems only Kp by tau s plus 1 is the transfer function. So basically, so this is your input and this is your response. Can you find what is transfer function? So basically you can find the transfer function. The transfer function is nothing but Laplace transform of t into e power minus t divided by what is the input x of s, which is 1. So this is the response for this input. Then you can find the transfer function. So basically these three are linked. If you know input, if you know transfer function, you can find the output. If you know the output, if you know the input, you can find the transfer function. So what is the transfer function is 1 by s plus 1 whole square. So basically what is the transfer function is 1 by s plus 1 whole square. Then what is the response? What is the response of step input is nothing but 1 by s into 1 by s plus 1 whole square. 1 by s into 1 by s plus 1 whole square. So what is the response is equal to 1 by s into s plus 1 whole square. So how do you write here? Split into partial fractions. A by s, b by s plus 1, c by s plus 1 whole square. So this is my step in. So what is my capital Y is Laplace inverse of A by S, B by S plus 1, C by S plus 1 whole square. So you have to split this into partial fractions. If you split this one, you will get A1, B minus 1, C also minus 1. So the answer is 1 minus e power minus t into e power minus t. So this is the response. This is the step response of an unknown process. Now basically if you see here, when I have a system input 1, I am getting t into e power minus t. So 1 by s plus 1 whole square is the Laplace transform. So basically Laplace transform of t into e power minus t divided by 1, which is already x of s, 1, which is nothing but your 1 by s plus 1 whole square. Now same system 1 by s plus 1 whole square, if I force it by 1 by s, then what you will get is 1 minus e power minus t into t power minus t. Here Laplace transform of 1 minus e power minus t into e power minus t divided by 1 by s. This is also equal to 1 by s plus 1 whole square. So basically Laplace transform of output divided by Laplace transform of input in its deviation form is nothing but your transfer function. So this is the output response for this input. This is the output response for this input, but all are linked. Now let's understand what is tau. Tau is called as time constant. Tau is called as what is time constant and what is the significance. What is the significance of tau? So let's take two transfer functions, 1 by s plus 1 and let's say 1 by 2s plus 1. So let's say if you force both the systems by 1 by s, can you sketch the response? Let's say y1 here and y2 here. Y1 and y2. Can you find what is the response in both the cases? So what is y1? So what is y1 is 1 into e power minus t. What is y2? 1 into e power minus 2t. Suppose can you find what is the response? What is y1 after 0.1? What is y2 after 0.1? So what is y1 after 0.1? This is 0.095. So what is this one? Point 18. What is final value? 1. What is final value? Here also 1. So if you plot y1 and y2 on both, single graph. The ultimate value of both the value systems is 1 only. Both the systems ultimately reach 1. But if we sketch the response of y2, it is slightly slow, whereas y1 is fast. Because at point 1, this is 0.095, this is let's say 0.18. So y2 is faster than y1, but their ultimate values remain same, y1 and y2. So this is response as a function of time. So basically what is the importance of time constant is, so what is tau 1 is 1, what is tau 2 is 2. So the second system time constant is 2. Time constant helps to reach the response faster. Time constant helps to reach the response faster. So, where this time constant is high, the systems are fast, our systems are sensitive. So, time constant high means systems are sensitive. Time constant high means systems are sensitive. So the importance of time constancy is it tells you how fast you will reach the response. So in the both the cases, so the system where time constant, which here the system with 2 is faster, because for the same reading here, so when you have a time constant 2 for the same time at 0.1 minutes, your response is only 0.09. Whereas here the response is 0.18. So y2. So the systems are faster. Systems are sensitive. So the response of y2 is higher than y1 because the time constant is higher for y1, y2. But ultimate values for both the cases are same. The ultimate value for both the cases are same, 1. Sorry, any mistake in the here? Oh, it is t by, this is t by 2, no? Can you check the answers again? Yeah, 0. I think 0.05. So I think the entire discussion that we have done is wrong. So I'm just deleting the entire things. So just delete the entire things here. So basically, so their ultimate values are 1, but y1 reaches faster, y2 is slow. Y2 is slow, y1 is faster because time constant is low. So the statement is time constant low means systems are fast or sensitive. So the response of y2 is slower because the time constant is higher. This is tau 2 which is greater than tau 1. Tau 2 greater than tau 1. So time constant, small time constant or low time constant means systems are fast. So time constant less means systems are acting quick, our systems are fast, our systems are sensitive. So systems are sensitive. So importance of time constant is less means systems are fast, our systems are sensitive. Now KP is called as steady state gain. KP is called as steady state gain. So what is the importance of steady state gain is, I'll take two systems, let's say 1 by s plus 1 or let's say 2 by 2 by s plus 1. 2 by s plus 1. Both are forced by 1 by s, 1 by s. What is the response here? Y1 equal to 1 minus e power minus t. What is y2 equal to? 2 into 1 minus e power minus t. What is y1 of infinity is 1. What is y2 of infinity is 2. So basically what is steady state gain is, if you give 1 unit change in the input, how many units the output is gaining is what is steady state gain. So here I have processed 1 unit change into the input, but when it is coming out, the output is also 1 unit change only. The input is changed by 1 unit, output is also changed by 1 unit. Whereas here input is changed by 1 unit, output is changed by 2 units. So basically, when you change the input by 1 unit, how many units the output is gaining is basically the concept of steady state gain. So when you change the input by 1 unit, how many units the output is gaining is what is called as steady state gain. So steady state gain here is 2, here it is 1. So that is why the system is gaining 2 units here, whereas system is gaining only 1 unit here. You have the FM class at 7:30. Okay, so then I think we have left with only 10 minutes. So I'll take the doubts for this 10 minutes. Today evening mostly we will not have any class because I have meetings till 7 o'clock. But if there is any update, if I am free, I will inform you by afternoon. See, I want to take why I have written, let's say 2 by s plus 1, because so 2 by s plus 1, because I just wanted to show you the difference. Steady state gain affects your final value. Suppose now let's take this system Kp by tau s plus 1 divided. This is A by S. This is what is the response that you are getting, Kpa into 1 minus e power minus t by tau. Suppose if this is my response. If you sketch the response y as a function of time, what you get is, this is my response. What is the final value? Final value is, what is phi of infinity? Kpa into A. Kp into A. So if you see, tau has no influence on the final value. Tau has no influence on the final value. The final value remains same, which is Kp into A. The final value is Kp into A. Final value. So tau has no influence on final value. Then what is the importance of tau? Suppose if you see the, just find dy by dt. Dy by dt at time t equal to 0. Then what you get is Kpa by tau. So the slope here, the slope of the initial value is Kpa by tau. So if tau is low, then slope is high. Slope is high means system is fast. So if tau is low, slope is high, that means systems are fast, are sensitive systems. So if tau is low, then slope is high, that means system is fast. So basically, tau helps to reach the ultimate value. To reach the ultimate value. So basically, tau is low means fast systems. Systems are fast because the slope is Kpa by tau. So here we are talking about slope Kpa by tau. Maybe I'll take you to this example here. What is y1? What is the response y1? 1 minus e power minus t. What is y2? 1 minus e power minus t by 2. So what is dy1 by dt at time t equal to 0 is 1. What is dy2 by dt at time t equal to 0? What is this slope? What is this slope? 0.5. The slope of y1 is 1. The slope of y2 is 0.5. So because this when this time constant is high, the slope is less. That means systems are slow. Understood? So what is dy by dt at time t equal to 0? What is dy1 by at time t equal to 0? Here the slope is 1, here the slope is 0.5. So when the slope is 1, the systems are fast. When the slope is 0.5, the systems are slow. So basically, have you understood the importance of Kp and tau? See, these derivations are also important. Reason because, no, I just wanted to show you the effect of Kp. That is why I have taken the transfer function 2 by s plus 1. So from this transfer function to this transfer function, only there is a change in Kp. So that you will come to know the effect of Kp. So basically, ultimately, so this is important. So the final value has no effect, or tau has no effect on the final value. But tau has an effect on the initial slope. If tau is low, then the slope is high, then the system is fast. So okay, you can take then 5 minutes break and you can join the FM class. If you have any doubts, I am here to clear your doubts. So you can't have any, let's say, which should be more or less. It is a system driven. Suppose if you take a liquid level tank, first example, the Kp is R. If you take thermometer, Kp is 1. So you can't do anything with that Kp and tau. They are related to system. So sometimes some systems has a tau 1, some systems tau has 10. So it is basically the inherent characteristics of a system. See, partial fractions is something that you have to learn on your own. So there is no trick here. But this is something which is important for PDC.